My name is Yang Zhizhu, a faculty member at the Terasaki Institute. Today, our first speaker is Professor Joseph DeSimone. So Professor Joseph is a professor of translational medicine and chemical engineering of Stanford. He is also the director of the Stanford Precision Health and the Integrated Diagnostic Center. So Professor Joseph has already published over 380 scientific articles and also holds more than 213 issued patents. So he has already achieved so many incredible achievements in green chemistry, nanomedicine, medical devices, and 3D printing. So he's also the co-founder of several companies based on his research. So I'm very looking forward to Professor Joseph's presentation. The floor is yours.
Thank you. Well, it's very nice to be here in sunny Southern California. But let me just first say that I have been watching Professor K's career for a long time. And I have been extremely impressed by the breadth and depth of his research, and also your confidence and guts to do unconventional careers. And I've always treasured that. And but congratulations on all the progress here. It's absolutely stunning. I'm new to California. I started at University of North Carolina, Chapel Hill in 1990, and I'm an East Coaster, and I had a great run there and worked with a lot of students. My first PhD student, I was the new president of the University of Maryland, Baltimore County, Valerie Ashby, after leaving Duke University. And at the end of the day, this is all about great students and activities, and we've had a lot of focus on translational work in a number of different ways. I'm not going to go into much of this. I may touch a little bit of what we did at Liquidia in passing, but after in 2014, I left Carolina to lead a 3D printing company, Carbon, and I promised the investors I would do it for a year. I ended up doing it for 6 years. And ended up shutting down my program. And when I got my life back, I ended up staying on the West Coast. So I'm now out at Stanford. I'm on the board of National Geographic, and I'm chairing my alma mater's board, Ursinus College outside Philadelphia. And we've been able to assemble a great group of students. And the difference now at Carolina, so Carolina doesn't have a school of engineering. I know most people don't appreciate that. It's the oldest public university in the United States. And so and I'm a chemist, and my group was 90% chemists and 10% engineers. Now at Stanford, I'm in chemical engineering and the School of Medicine, and my group is 90% engineers and 10% chemists. So it's been a big swing for us. And so representing all the different disciplines of engineering, from bioengineering, material science, chemical engineering, double E even, and chemistry, and a really terrific group of students and postdocs. Kai Wynn is on the circuit now for interviewing, got a couple offers, and a great group of undergraduates and staff, and then some colleagues at Chapel Hill that we still work with. The research is funded by the Bill and Melinda Gates Foundation and Wellcome Leap and NIH and the Shanahan Foundation. A number of collaborators. Kurt Frank has sort of adopted us, and he's in our group meetings all the time, and I'll talk about some work with Eric Schachve, and a point to some work with Heinrich, but these are various folks that we collaborate with in different ways. And just before to get started, if you go to our website, we're really intentional about our values. We want to make sure that people realize that we can be a destination for excellence wherever it lives. And you can read more about this on our website and what's important to us. So we heard a bit of an introduction last night from Chad about making things, and I thought I'd put it into context a little bit regarding the 3 different ways of really making things: the molding, formative techniques, which we've been active in over the years. I'll touch on that. A lot of people make things by subtractive techniques, and and then additive. And I think the value of doing things by additive manufacturing is mostly related to making things that at scale that cannot be made by molding. The complexity of lattices, for example. Lattices are an integral part of manufacturing this building and bridges, but every strut of a bridge is an individual part. And but to do that as one component is impossible from a manufacturing point of view. And so additive really thrives in that regard. And just to say something very simple but exceedingly profound, product design depends on product manufacturing. You don't see things that can't be made. You do research, there's a lot of academic research, you see lots of beautiful things. But translating that into the market requires it to be makeable. And so this difference between a product and prototyping is really important to keep in mind. And what I'm going to try to emphasize is what I would call manufacturing science and engineering, the tools that can actually scale to bring things forward, as opposed to the beautiful tools for prototyping and basic science research. And in this context, I stole a slide from Matt Becker, his perspective on polymer-based additive manufacturing shown here, with the various techniques, including the extrusion techniques that we see a lot of. Think about like a hot melt glue gun and other sorts of extrusion kinds of approaches for deposition in that manner. And then you have jetting, binder jetting approaches with UV curing and powders, and then powder sintering, which really comes out of the metal-based 3D printing world. Metals being atomic solids sinter very differently than molecular solids. Polymers derive all their properties from chain entanglements, and they often don't, the full evolution of chain entanglements often doesn't happen by sintering. But it's a profound technology nonetheless. And then what I'm going to be talking about is the liquid-based UV curing systems, and there's been a history of those. Basically a direct write tool in a layer-by-layer approach, turning a liquid into a solid. That was the SLA technologies developed in the 1980s in Japan and then further in the United States. And then going from direct write to an XY projection, a DLP system, digital light projection systems, which dramatically improve the speed because now you're projecting an entire XY plane instead of direct write. And then our take on this, and I'll walk through this, that we call continuous liquid interface production, which is a combined bottom-up approaches, although this can be bottom-up as well. But we have a breakthrough in a window technology that really is focused on mass transfer, not adhesion, as often you'll hear some people talk about, but mass transfer, because these reactions and processes are mass transfer limited, not reaction rate limited yet. And I'll talk today about two pivots of this work related to high resolution and a new type of clip that we'll walk through. So about 7 years ago now, we published this paper and gave a talk at TED about a new approach for 3D printing that Matt we refer to as continuous liquid interface production. So it's basically a XY projection from a DLP projector, and we're using light at 385 nanometers. At the bottom of this reservoir is a very special window. It's not only optically transparent, but it's also permeable to oxygen. And oxygen, those of you who are familiar with free radical polymerization, oxygen's an inhibitor for free radical polymerizations. When you hear about polymerizing a monomer, you often degas the monomer. Well, you're removing the oxygen so that you can kick off the polymerization. Here, we're exploiting oxygen. And we're exploiting the inhibition of the polymerization and the replenishment of oxygen caused by the depletion of oxygen with the light-induced decomposition of the photoinitiator. I'll walk through that in more detail. So what happens is you lower this platform into this liquid reservoir, you get very close to the window, and let's say you get close to about 100 microns. So you have a 100 micron sandwich of UV curable resin between this stage and the window, and then you start projecting light. And what happens is that light will permeate that 100 micron gap, will cure the resin asymmetrically. The resin will bond to this metal platform, adhesively bond to it, but it doesn't bond to the window because of the oxygen replenishment, and there's a gap between the part and the window, And as you pull the part up, there's a suction force that draws resin in underneath it. And as this platform, and this is an accelerated video, but this is 100 to 1,000 times faster than traditional 3D printing running in this manner. And because we're using this projection of light, we can basically make unmoldable things. And this breakthrough in speed allowed 3D printing to transition significantly to a manufacturing setting. Now, what kind of window gives you these properties? Well, we looked at a lot of different kinds of windows. We looked at thin films. We looked at rigid windows. We looked at liquid windows back in 2014. Chad talked about some liquid windows. We were doing that in 2014 as well. The key is that they're highly permeable to oxygen, and perfluoropolyethers and perfluoropolymers are among the most oxygen-soluble or permeable materials known. We like rigid windows because there's a lot of forces on the growing part, and I'll walk you through those. There's a Stefan adhesion force between a solid and a window that's caused by the liquid. And so we actually like mechanically strong and durable windows to make this to work well. So I'm going to show you something here. This is optical coherence tomography, kind of like ultrasound imaging, but uses light instead of sound waves. And you'll see the part growing. We put some particles in there as a contrast agent. But you can see this gap. This is a gap created by the oxygen. Light's coming through here, curing the resin, and you see as you lift the part up, resin's being drawn in underneath here. This is not an adhesion issue. There's a mistake in the literature when people think about this as adhesion. This is a mass transfer issue. How do you get resin in to the deepest pixel? And that's the key to these processes. And oxygen gives you the ability to replenish liquid without going through a traditional layer-by-layer approach. So this is really a mass transfer issue. And so what's happening is, if you look at what happens, light comes in. This is a UV resin, a UV curable resin with a photoinitiator. Light comes in, it decomposes a photoinitiator, generates a radical pair. That radical pair can do one of two things. If there's oxygen present, the reaction with oxygen is far greater than it is for kicking off a polymerization. So there's a competition reaction between inhibition with oxygen and initiation of a polymerization. And only when, and so when light comes in, so this is a concentration axis, general terminology, and this is a z-axis, so we're going from the window up into the liquid. Light's coming through the window. It's most intense as it enters the vat, and then the light intensity depletes with distance up into the liquid just due to molar absorptivity. That light is decomposing the photoinitiator, which generates a radical pair, so the radical concentration is highest at the window, but so is the oxygen concentration. And as that oxygen concentration gets depleted because the radicals react with oxygen, the oxygen is being replenished through the window because the window is very permeable, and underneath the window is a source of oxygen. And so what happens is the oxygen concentration is dropping with time, with distance, and once it drops below a certain threshold, the polymerization will take off. And this distance is the dead zone. And that's where the rate of polymerization will take off. There's a gel effect, even a Tromsdorf effect, back to Smith-Hewitt kinetics. And this distance is what we monitor. There's a lot happening. There's heat evolution, there's oxygen consumption, viscosity issues play a really key role. There's a lot of forces on the part, so the green strength of the part as you're pulling on it, and this is just a simple geometry. I'm showing you just a cylinder, but imagine if you're making a complex lattice and the part is elastic. You can deform it and screw it up. And so there's a lot, this is a complicated process. I think of this as a software-controlled chemical reaction to grow the parts, because we have to bring a lot of understanding to the process to even get it to work. And so we have this flow field driven underneath the forming part. There is a gradient of polymerization between the low viscosity monomer and the part, and there's a velocity flow field, and we control every step of the process. The printer is designed with the principles of mechatronics, where everything is sensored up, motorized, and completely controllable. And so when we elevate the stage, we can elevate it at whatever rates we want. We can pause wait for the liquid to reach quiescence. We can photolyze an image, and then we can repeat the process. And this can happen very quickly, and we're basically playing a movie frame by frame, okay? So we rolled this out into a company. It was a fun run leading the company. The first person I hired, our founding VP of engineering, happened to be the founding VP of engineering at Tesla. We had over 50 former Tesla employees in the company. And we sensored up the printers, and we connected them to the internet. And reason is, in the beginning, this was hard to get to work. And our fundamental understanding, the digital twin of our process, if you will, was modest. And we could screw up any print. But what happened was we could do over-the-air software upgrades. These printers were connected to the internet. We controlled the oxygen, the light, and everything. And as more people used the printer, the better the printers got. That's a network effect. And it turned out to be an amazing way to roll out the business. We started streaming together the printers. And again, with everything connected, even the printer platform has got a near-field communication tag on it. So we're moving the platforms around these factories, and the software's tracking every element of it. And so you knew which parts were on which platforms. We could print the parts. We can go into there's a part washer in this schematic. This is a part washer. These are parts being printed. And you can start putting together bigger and bigger factories. And even with bigger and bigger printers. And so this is what a factory floor looks like. This is outside of Shanghai, and there are multiple big factories making everything from Adidas running shoes to football helmets and dental models, and it's remarkable to see. And it's dead quiet. It's light, making these parts, and you don't have to have every printer making the same thing, right? So there's a lot of control of how one keeps a factory running at a capacity. And one of the things to recognize is when you start running up lots of these printers in a liquid resin, it's not uncommon, or in fact it is common, to wash with solvent because there's a lot of excess resin on the parts, and you can't do that at scale. That's a waste nightmare. Mixed waste, IPA, resin, And so we ended up doing is pioneering a spinning process. And so you'll see a centrifuge designed in the Central Valley, California, like a lettuce spinner, a platform with a pair of running shoes with a lattice. And so these parts come out of the printer and they get spun. Excess resin gets collected at the bottom and goes back into the printer. So it's 100% atom efficient from this process. And back to the digital world I'm talking about, these shoes are not only designed for performance and comfort and all those things, they're designed to be spun clean. That's what a digital co-design process looks like in the digital world, to optimize manufacturing and throughput. And then every part has got a digital code on it, a data matrix, and it's tracked throughout the factory. So this opens up new business models. I think of every part as alive. Every part has a unique record in the cloud. We have its birth certificate. We know which printer, which resin. We know every photon that went into every layer, all documented. We have its grades in school. We have its mechanical properties. That stress strain curve gets put up into that file. They go through use life. You can measure the properties again and populate it. You can get its death certificate and recycle. You can use this data to now quantify environmental stewardship. And this digital world opens up new business models. And this is where this is all going. So let me pivot away from the process and talk about the resins. As a lot of you know that are in the polymer world know that light is not a great way to make great polymers. They're often brittle plastics. And it doesn't matter if you got a really fast polymerization process, nobody wants lots of brittle plastic stuff. And so and I'm a polymer person, this was a key, another breakthrough we needed to focus on, is how do you get a great set of polymer properties out of a light-based printing process? We cheated. We broke it into two processes. Most great polymers are made by reactive resins. Think about polyurethanes, polyureas, cyanate esters, epoxies. So we basically split the process into two. And we use orthogonal chemistry. You saw Carolyn Bertozzi just got the Nobel Prize for orthogonal biochemistry inside a cell. This is orthogonal chemistry in a 3D printer, right? So we have free radical chemistry, a photoinitiator, and classic free radically polymerizable monomers. Think about it as 10 to 15 volume% of a UV curable component. And then we have classic step growth polymerization components, shown here with an epoxy, a diapoxide and a diamine, with a certain pot life. We knew no one ever went into this approach because the printers were historically too slow, and these step growth chemistries would prematurely gel. We're printing 100 to 1,000 times faster. We knew we had a window of operability to combine both step growth and the UV curable systems. And this orthogonal chemistry allows you to print the part. Now it's mechanically weak. It's 10 to 15% of a network and 85% of a step growth monomer, right? And all the forces are different. You have to control that with the software. But then you basically go through a solid state polymerization in the form of the part. And this is how this works. I showed you epoxies. I love polyurethanes. Your polyurethanes are really versatile. You can vary the soft segment, the rigid segment, the chain extender. You can get elastomers. You can get the high molecular weight linear polymer that's got great ductility and impact strength. And we use these a lot in this approach. And in the beginning, as I mentioned, we pioneered this kind of chemistry, but we started to teach the chemical companies how to do this. And so we set up basically an app store for resins. And right now, there's over 50 different resins available. We designed about 2/3 of them and stood up a supply chain. But now the chemical companies are designing resins for this platform, and they sell them on our platform. They handle all the shipping and those details. And it opens up new properties that we haven't gotten to yet, especially in the dental space. I'll walk through that. But we have master files at the FDA and all sorts of products with a wide range of different resins, and we're constantly developing new ones, including resins that are chemically degradable, can go back to liquids and reuse them. And so lots of stuff coming. And so this is now a platform approach, and it gives businesses the ability to make things, and I've got a little video just to show you this.
We salute all those who believe good enough is never good or enough. Those who pursue excellence for themselves and for our planet. At Carbon, we apply our craft using science and technology to push limits and realize products unmatched in performance. Our difference is one you feel, and it is light years ahead of anything else out there. You feel it in running shoes that control energy with every stride. Saddles that enhance your performance and comfort mile after mile. Helmets that increase your protection every time you take the field. Clear aligners and dentures that improve oral health and give you more than a few reasons to smile. Crafted by Carbon is a promise. It stands for dedication and focus to crafting what you and our planet truly need. Ongoing creation of amazing answers to our toughest questions. We salute the leaders, dreamers, and doers who keep creation in motion, who boldly imagine a brighter future and craft it every day.
So this is an amazing business. No printer has been taken out of the field. They're all in a subscription business. They all consume lots of resins. They consume software too. And we started with, I always rank things in a hierarchy of regulatory hurdles. If you can design a running shoe and you know it works, you can scale it. Way different than the automotive industry or the healthcare industry. So we always stage things to get adoption and like that. And these running shoes represent a unique moment in additive manufacturing. This is the highest volume 3D printed product in history. We went exclusively in the beginning with Adidas. Adidas makes 500 million pairs of shoes a year. We'll get to 10% of that. We're not there yet. But we know there are more 3D printed shoes with Adidas made than all that Under Armour sells in total, because Under Armour is not a real player relative to Nike and Adidas. And we started moving, and we got the first 3D printed parts on new vehicles out of Detroit, on Ford Mustangs, F-150 trucks. We got parts on all sorts of electric vehicles around the world, all sorts of industrial components. And I want to spend a big fraction of our business is in healthcare. related to dental. But these products become, we think of things as a bowling alley. From a marketing tech perspective, what's the first bowling pin you're going to knock over? And then how does that cascade to additional products? These elastomer lattices, pioneered with Adidas, that are energy returning, you can make a version of it that's energy dissipative, which you want for football helmets. But the designs are similar, and some of the mechanics are similar. And so these are a wide range of products that are scaling in this manner. But digital dentistry is an amazing field. It starts with things like Invisalign's product. Invisalign created a category. Their patents expired. They now only have about 50% of the category. We power about 70% of the others. But we also pioneered the world's first FDA-approved 3D printed denture. There are 36 million Americans that have no teeth. There's over 100 million Americans that are missing a tooth. This is a huge upward mobility issue. It's hard to get a job if you don't have your teeth, speak properly, eat properly. This is significantly cheaper to go down this pathway, and it's enabled by intraoral scanning, digital, getting away from impressions. And we've got a video to show you what dentures are like.
For the last 45 years of delivering dentures or longer, there was always an unknown. When patients are looking for a denture, their biggest complaint is that they don't fit.
You think of denture making as a craft, I need a craftsperson. And carbon can do it.
Taking a lot and making it less is what a mill does. Taking nothing and making it something is what a printer does. We don't want to make molds, we don't want to make jigs, we want to make final products. And when you make final products from the milling process, it is far less economical than when you make final products from the printing process.
There's three basic things. There's fit, there's comfort, and there's function. 3D printing brings all of those together. The accuracies and fit, comparably speaking to what was done even 5 years ago, has become so much higher in impact for patients and for clinicians across the country.
For somebody that makes dentures day to day, it's transitional, it's transformative. A lab powered by carbon will allow me to make probably the best denture ever made.
So of all the things we're doing, I'm most proud of that. And you go from 8 chairside visits for a manually prepared product to 2 chairside visits. And it's perfectly fitting because it's done with scanning. If you lose your dentures, and I've heard so many horror stories, somebody wraps them up in a newspaper, throws them in a fireplace, dog gets them. You're back in that chair 8 more times to get another one, handcrafted. It's hard to hire handcrafting people to make them. Once you go digital, you could order a 4-pack. Doesn't matter, right? So it's transformative in that regard. Okay, so that's history. When we look out forward, and what are the additional things that need to happen in this field? One is we still want the printers to go faster. We want to do multiple material printing. We want to go to high resolution. Lots of opportunities on resins that are electrically conductive, resins that are biodegradable, resins that are chemically recyclable, new kinds of properties, thermal conductivity. And then there's lots on the software side of things. We spend a lot of time on the OS or the operating system, but all sorts of scanning and design software too. Let me focus on high resolution for a second. Beautiful things happening at the small scale with direct write tools. You saw some of this in Chad's talk last night. Think about nanoscribe tools and everyone, amazing things. You can't scale those up. They're research tools, and they have an important role in our ecosystem for doing that, but there's a lot of interest in how do you scale these things up. And so we set out to design a single-digit micron resolution printer. So the printers I just showed you from Carbon, there's 2 classic sizes. There was a 75 micron pixel, it's the M-class printer. And there was the larger printer for the running shoes, it's a 162 micron. So we've built printers now down to 30 and now 1.5 micron resolution. And what that involved, what Kai Wynn and Brian and Tim focused on, was the projection optics. Again, the fluid mechanics are very different at this length scale. The reaction kinetics, in situ process monitoring, and the software. And we like to print the Eiffel Tower. That's sort of a fun thing to do. The classic carbon printer, 75 micron, 30 micron resolution. We can start making these things. And then you see this little guy right there. This is done with a 1.5 micron XY projection. And you know, when you start putting this together and back to manufacturing, science, and engineering, you think about resolution and speed. Here's a lot of your direct write tools down here that drive a lot of the research industry. We want to start going into this box and have high throughput, high resolution. And that's where we're spending our time. Well, what are some of the things that we can do with this printer? Well, Ali and others know, we used to, and Samir Minagachu, we used to make particles. I love particles. We used to mold particles. Now we're 3D printing particles. And when you have particles, you always have to think of a web-based process. You need the throughput. And so we have film that comes through the printer, the high-resolution printer, because it doesn't take long to print these. They're not very big. But you want to make a lot of them, so you got to get the film going. And these are some of our particles. So this is actually looking at our particles in Heinrich Jaeger's lab at University of Chicago. He traps our particles in a sound node, so we can inspect them individually. But these are really interesting objects. And I used to mold particles. We call that particle replication non-wetting templates print. And I talked a big game. But you know, at the end of the day, looking back, I think we had 10 different shapes. Because it was hard to get the master template. And you invested a lot in that. And because of the symmetry challenges with molding, we had modestly interesting shapes. So we're printing these now with light, but they're also moldable at that class with single-step molding. There's really interesting shapes that we never actually did with the print world that required two-step molding. And now we're molding these kinds of things, but these could be moldable. I think you'd pay in an arm and a leg to try to mold those, but we could do it. And now we're molding things that are unmoldable, or making things with light that are unmoldable. And we think this is going to open up all sorts of interesting opportunities using light to make objects. Where else are we interested in these? A lot of beautiful work coming out of here in microneedles. A lot of the world's chasing intradermal delivery. Why isn't intradermal delivery a thing? Well, it's been a challenge. Making it a reliable and repeatable dosage form. Mark Prowsens, I'm glad to see him here, one of the leaders in this space. Lots of amazing breakthroughs in understanding the value of going intradermal delivery. And part of the reason is we have 100 times or so more migratory immune cells in the dermis of our skin than you do in muscle. But you know, an injection into the muscle is a reliable, repeatable dosage form. It doesn't take a lot of skill to dump everything in a syringe barrel with one shot and get it into the muscle. But it takes a talented clinician or physician assistant to get it in the intradermal space. And if you're putting liquids into that space, large volumes of liquid, that can be painful. And you know, when monkeypox broke out and it was on short supply of the vaccine, they went intradermal. But it was a challenge getting that vaccine into that space. So lots of people are interested in this world. In perspective, I think the evolution of the microneedle world started back in the 70s, and a lot of the technologies were etching silicon and some of the microfabrication techniques out of the microelectronics industry. Arguably, you can call that Gen 1 technology. And then there was the molding approaches. Start with a master template etched in silicon, make a mold, replicate those features, reasonable fidelity in the replication process, but opened up the material space. But you're still limited with typically features that are all the same height, because that's what you get out of microelectronics industry, and you have a bed of nails effect challenges, the higher forces. You still have limited designs, and I would argue that we're now into a Gen 3 microneedle world that allows you to go to designs at scale, not just prototyping, but now at scale with designs, even simple designs of different heights, different structures that you can directly print. So we've been at this now for a while, and finally got to the vaccine world when I moved to Stanford. But we started off with these very simple designs, arguably designs that could be molded, simple designs, maybe a little bit more surface area. This is a printer with 30 micron resolution. And we did a free meniscus coating, dip coating of a model a vaccine component, antigen and adjuvant. We separated them on different needles. And then we did a skin delivery system. And we compared that to intramuscular injection, like a lot of people are doing. And we showed that because we're taking advantage of a higher concentration of migratory immune cells in the skin, we saw a 50-fold increase in antibody response compared to an intramuscular injection. We had a different Th1, Th2 balance, T-cell, B-cell response. I won't get into those details here, but we showed that this is a valuable approach for an enhanced vaccine delivery system. The challenge is when you have a coating on a solid microneedle, and especially some coatings that might be not mechanically very strong, think about a brittle sugar coating from a lyophilized-like product, and the analogy I talk about with the group, think about a 2-day-old glazed donut, right? The sugar falling off. If that sugar is on the cone and you're pushing in the skin, that can slough off as you're inserting it and lead to the lack of reproducibility and reliability. So now with a higher resolution printer, we can start advancing these designs to designs that arguably haven't been seen before and take advantage of a structure, a mesoscale structure within the needles. With a 1.5 micron pixel and doubling the pixel size, we found out what was an optimal size for us, and we've been making a lot of different designs. And now we have the value of a light-based process that the innovation engine is ramped up, because the kids can design something in the morning, print it out in the afternoon, it just opens up the design space. We're really interested in having this innovation capability to make microneedles a reliable and repeatable dosage form. Now what's cool about these lattices, they're really great at trapping droplets of liquid through interfacial tension. You can control the surface energy of the lattice, trap a drop of liquid. Now you could deliver that liquid to the skin then. And so we've been taking the Moderna, Pfizer vaccines and doing a local delivery without changing the formulation at all, just a different delivery mechanism. But we also like to lyophilize the products. And lyophilized products in a dry state, the lipid nanoparticle mRNA vaccines at room temperature in a solid form have been shown in the literature, not by us, but in the literature, to be room temperature stable for 3 months and 6 months stable at 4 degrees. So it can dramatically change the supply chain, and the idea is that you could have a dry product inserted into the skin and have your own interstitial fluid reconstitute the product. And that's the goal, to be able to ship dry products that are more shelf stable for the vaccine world. We've been working on excised pig skin, doing transfections with both liquid and solid products, with LNPs, with reporter genes. This is just M-Churi. And we're seeing the LMAPs, the lattice microneedle arrays, even doing better than an intradermal injection. Well, why is that? Well, it looks like we're delivering the same dose, but we're spreading it out over a larger area. And there's some really interesting vaccine kinetics we're looking into where, think about, do you want to give 2 immune cells 100 nanoparticles? Or do you want to give 50 immune cells 2 nanoparticles? Because you can saturate out the protein expression. And it looks like we're in this regime where, we're starting to quantify better performance, even over intradermal injection, because we're giving access to these migratory immune cells. So we're going from excised pig skin, then the team traveled to Iowa, and we're just inoculated 70 different pigs, and we're ramping up, so the story is being told. And we got all sorts of new designs. And we're looking at different ways of delivering and different components, and we're trying to establish a nomenclature. I'm not sure where we're at yet, but this is where we're going. We can also bring in advanced materials that have capabilities of deformation, like a living hinge. And so we've got all sorts of new products coming out, new designs, where we have moving parts into the microneedle world. So stay tuned for this. But again, things you can't imagine if you didn't have this capability for making things. Hold that thought, I'm going to come back to that. Let me tell you about a new type of 3D printing we call injection clip. So clip, as everything I told you, excited about, it's a mass transfer limited process. You got to get liquid into the gap. It's not a reaction rate limited process. There's no heat dissipation challenges. This is still a mass transfer limited process in all the SLA technologies. So how do we get this closer to a reaction rate limited process? Well, we got to get more resin into the gap. And so, we're limited of resin coming in underneath that part, all coming from the periphery of the part. Well, what if we were able to mechanically inject resin into the gap, not use suction forces, but now have a dynamically created microfluidic channel in a part that was fluidically connected to a port in the platform with a mechanical injection of resin. Now you can blow resin into that gap as fast as you want. And you can imagine the design software for what can the channels look like. And you can also imagine multiple resins. Okay? So we call this injection clip. This should get us another order of magnitude or more in enhanced speed. It should open up higher viscosity resins and composites and multi-material printing. So we just published on this. And in working with Eric Schachve and understanding all the details in the fluid mechanics. And what's fun is you can basically toggle some gradient between clip and I-clip. Imagine building a part where you fed 20% of the resin via the channel and 80% was drawn in from the periphery. Or you fed all the resin via the channel. And so you can run this process. Here's an example where all the resin needed for the part is coming through that central port. Well, here is where we're delivering just a fraction of the resin through the central port, and some is coming from the periphery, and you get a stagnation zone underneath the part, which has some really beautiful fluid mechanics interface at the stagnation zone, and you can toggle through that. But the most important thing about this process is this Stefan adhesion force. If you have two plates of glass and you have a drop of water between them, it's hard to pull a glass apart. It's easy to slide them. But we're basically pulling in the Z direction two solid surfaces with liquid between it. That's what draws the liquid in. There's a lot of forces on the part. So much so that you have to balance that with the simple work of adhesion of the part glued to the platform. And if the adhesion between the part and the window caused by that liquid gap exceeds the work of adhesion in that area, the parts can fall off the platform to failure mode. And depending on the width of the part, that adhesion force is higher. So here's where the diameter is very high. You pull the platform up. We put a load cell on the platform, measure the loads, the forces. You pull the platform up, you stop, and you wait for the liquid to fill into the gap. And there's a stress relaxation that takes place. Depending on the diameter of the part, as the diameter goes down, the forces are lower. But look what happens with injection clip. Those forces can go away. In fact, you can get a negative force. This is like walking up to a wall with a fire hose. You're getting pushed back the other way. And so the forces go away. Well, why does that matter? Well, in 3D printing, it's often needed to put supports on parts, to hold the part onto the platform, right? Now you can do things where you don't need that as supports. Now, if you have islands, you'll still need a support, depending on the design. But now we're designing all the software to innervate inside the part where based on fluid mechanics and forces, where you need to send the resin. It's all software controlled. And where you no longer need resin, the software will close the port. And it's fun to watch the resin shutting off and being shuttled into other areas. It's all software controlled. So we got students who are just designing all this software. And you can imagine that channels can get increasingly interesting, and you can start feeding multiple resins. Now, we started working on this before the war broke out in Russia and Ukraine. We chose iconic buildings. We want to keep with 3 colors. So it's the same resin, just different colors. I'm from Philly. You're always going to see something from Philly, whether it's Rocky Balboa or Independence Hall. Paris, London, and St. Peter's Basilica. And when the war broke out, we added St. Sophia's Cathedral, but it changed our color scheme. But nonetheless, it was easy to do. And we built out the schematics for doing multi-material printing. And now we're feeding different resins using this approach. And I love this image, okay? But let me tell you what I think the killer app here is. And I always think about, what are the killer apps? The killer app here is actually the channel itself. One of the biggest problems with SLA 3D printing is something called overcuring. I talked a lot about you controlling the pixel size, but that was in the XY plane. The problem is the light, if you print this gap and you go to print the next layer, the light never stays in the layer you want only. And that's where you load it up with dye, you try to make it opaque. That means you got to put more light in. It becomes all sorts of problems. But making negative spaces in light-based 3D printing is an intrinsic challenge because of light, because there's resin here. It gets stuck in there, and you overcure it. And it accumulates light, and it will cure over time. And it's not just simple penetration, but there's light scattering coming into this space. There's light piping that's happening, depending on the design. It's complicated. Well, the resin that's coming through the channel is fully oxygenated resin. And you can feed way more than you need. And you can keep that channel open because it's not curing. And so just to prove the point, we have some of these fundamental unit operations from the microfluidic space. So microfluidics, as you all know, is a layer-by-layer approach. All the channels are rectilinear because you're projecting light in X, Y, and you're doing things vertically in Z. It's very hard to get a circular cross-section in a microfluidic channel, which, biology is circular. But the method of making has always been limited. So we vary these different channels. So in a vertical channel, there's no overcuring because you're just making a vertical channel. But when you start varying the angle, this is where the overcuring can take place, and we're going to increasingly challenged overcuring, including a horizontal channel. With traditional clip, we see, through our modeling that these will cure, and you look at a clip printed channel, we can make the vertical one, but we can't even make these others because of overcuring. But with iClip, we can keep these open. We can make negative spaces with this approach. And this is getting a lot of fun now. And it's trivial. You design something in the morning, you print it out. And so we're having a lot of fun integrating all sorts of different designs that are unmakeable with clip. And we're making microneedles with plumbing because we can. And it's getting really sophisticated, the kinds of designs that are opening up with this approach. And so this idea that we could be extracting interstitial fluid, we could be delivering things, we can be delivering multiple products, really think this is opening up this space because of this iClip advantage. And so let me just, sort of like a quad chart for DARPA or something, or ARPA-H, to be more specific. This idea of we want to mine 1 to 1,000 microns easily and at giga scale. Back of the envelope, 500 printers in a room like this can make 100 million products in 3 months easily. And this idea that if you could do that and open up this space of arrays, microneedles, microfluidics really opens up and can open up new markets. Phlebotomy. I'm going to get a little pithy. What if Theranos had it right? Now, you don't say that too much. You got to be careful. Except for the fraud. Put that aside. It's hard to put that aside. But they went after the wrong circulation system. They went after blood. And the opportunity, and beautiful, a lot of people here work this space. You know, we really want to use these tools to revolutionize how people access ISF. Working closely with my colleague Tom So with DNA optical biosensors, integrating those into these systems to go well beyond what you see with continuous glucose monitoring. And then clearly vaccine and drug delivery in this space. So that's how we're thinking about the future of this. Other things, where else is negative space useful? Columns, separation columns. Negative spaces at this length scale. And you know, how do people make negative spaces? Well, they pack solid stuff in columns and make negative spaces. We want to make these digital separations. Inspired by Buddy Ratner's work. Negative spaces. How do you do negative spaces at 40 microns? It's hard to do, right? We think we can keep, you know, so iClip and high resolution clip give us all three Cartesian coordinates, X, Y, and Z. And it opens up these kinds of ideas. So let me stop there. Big believer in digital fabrication. A lot of people have been talking about this, Industry 4.0 and all sorts of things. But the barrier has been able to, how do you scale things digitally? And having tools that can scale and compete with traditional manufacturing methods. And so if you can do that, we really, and the unmakeable isn't, and you can have end-use parts and end-use resins, economically, we really think there's a bright future. And then you think about a warehouse in the cloud and on-demand manufacturing and avoiding, you know, opening up local for local production, all sorts of stuff. So with that, let me end and thank you for the invitation and really glad to be with you this morning.
I'm always blown away by your work, Joe. It's absolutely amazing.
Thanks, Art.
You answered my question about how to clean parts from monomers, from the liquid. I think mostly it gets clean that way. My question has to do with your orthogonal reactions, say a urethane and a vinylic compound. That sounds a lot like interpenetrating polymer networks. And I'm wondering if you keep them separating in phases other than the IPN in order to get your final design of your products.
Thanks, Art. It's a rich opportunity of study and analysis, and you know, unfortunately, we haven't done much yet. You know, between the electron microscopy and the thermal analysis and dynamic mechanical thermal analysis, we just haven't done a whole lot. And I'm sure there's a rich morphology in there that we clearly can see, and how that changes with the process parameters and the 3D printing parameters and fillers, and so it's just a bandwidth issue. And but we'd love to get some of these parts in the hands of others that want to do some more things in that space, because it's really easy to make these. Mark.
You nicely described all the rate limiting barriers in the clip system and how you're overcoming them and getting even faster. What about the rate limiting barriers in the other approaches, and why are they intrinsically barriers that can't get to the speeds that you've achieved?
The other 3D printing approaches.
Non-clip approaches.
Well, any direct write system is going to be flawed. So that's all the FDM fusion systems. They're just going to be slower. Plus, they have anisotropy issues that are really significant. You know, the orientation of that layering. One of the things I didn't talk about, maybe Art was sort of getting at too, when you have a dual cure system, there's no memory of the layers, right? Because it's kind of like self-healing polymers, because you're curing resin. So we don't have anisotropy with dual cure systems. And so the anisotropy is going to be a latent issue for all the direct fusion systems. The sintering systems are pretty slow as one intrinsic issue. HP's had some modifications trying to speed that up. The challenge with a molecular solid, when you have a particle, let's say it's 10 microns, which is common, the chain entanglements within that particle are robust at the molecular scale. But when you have two particles sitting next to each other quiescently, and you heat them up for a fraction of a second, diffusion, there's not much chain entanglement that happens between the particles. It's not like convection in an extruder, which really evolves the chain. So these parts are intrinsically porous. Sintered nylon particles are like a sponge for water. That's why they haven't made the automotive transition, because they freeze and fracture. So there's intrinsic problems with these other approaches that have been historic. Somebody on the metal side needs to have a breakthrough in speeds, and most of it's gone in aerospace where the cost is just extraordinary and they can justify the slowness. But there's challenges out there, and we broke through, and somebody needs to figure it out in these other areas. I don't know what else to say. Yeah. Buddy.
Thanks. That was really great overview. Brilliant videos. The urethane chemistry. Moisture in the air degrades the urethane resins. How do you handle the difference between processing in southern Florida versus processing in Arizona?
Well, I'll go one other. How do we print differently in Denver than we do in Salt Lake City? Atmospheric pressure with a clip process is in the governing equations. But that's what's beautiful about software. There's an altimeter knowledge that goes in every printer. You just correct for it. On the chemistry, back to polyurethanes, as you know, polyurethanes have made a massive inroads into the automotive industry, other places, and there are ways of managing moisture in those applications, and we'll use the same approaches there.
Because the resins degrade so quickly in air moisture, so you got to.
But polyurethanes are used, all your new automobiles use polyurethanes everywhere.
Yeah, and to get reproducibility, you really got to exclude atmospheric moisture.
Oh, you mean during the printing?
Yeah, during the printing.
Oh, so we're actually using, most of these are blocked polyurethanes, and they're not free isocyanates. So they're blocked isocyanates, but there's some new resins that are cheaper, that are isocyanate based, that you have to manage the moisture, to your point.
Okay.
And a closed system allows you to do that with blankets of air, or dry air.
Yeah.
Great, thank you. Thank you.
Yeah, so let's have a coffee break and we'll come back.